Ever wondered why giants move so slowly in films? You're thinking to yourself, is this an aesthetic choice made by people who make these movies, or does this have some kind of foundation in reality? In this video we'll show that there really are real-world physical reasons for this, and we're going to have a look at a few of these now. The first thing we have to discuss is gravity. Now, gravity acts on all objects equally, so though it may seem counterintuitive, a heavier object will fall at the same rate as a lighter one. Oh, but you're thinking to yourself that isn't true. If I drop a ball on a piece of paper which is lighter than the ball hits the ground first. However, if you scrunch up the same piece of paper into a ball so it has less air resistance when it's falling, you'll see it falls at exactly the same rate as the ball. Now let's take another example. Imagine we watch a small yellow cube falling. That cube will seem to fall much faster than a much larger blue cube. However, if you watch both cubes falling together, we can see that they actually fall at exactly the same rate. So why does the small yellow cube seem to fall much faster than the larger blue cube? Using a simple 2D diagrammatic representation of both cubes, we can show why this is the case. When the blue cube has fallen a distance that is the equivalent of twice its length, the same distance for the yellow cube is 14 times its length, and therefore, relative to its size, the yellow cube appears to be travelling much faster. So what does any of this have to do with animation and animating large objects moving? Well, walking was once described this way. Walking is just falling and catching yourself. As someone walks, their waist rises and falls. We can see it here with the yellow box in place of the waist and the up and down movement of the waist. When someone or something larger is moving, their body will rise and fall at the same rate, but due to their scale, it will appear much slower. This brings me to the next area I'd like to look at, perspective. If you watch a block of flats being demolished, this looks very different to, say, a Jenga tower falling over. So why does the block of flats seem to fall so much more slowly than the Jenga tower? Part of this is to do with how far away we are from the block of flats when we see it falling. To return to our large blue box from the first example, let's see what it looks like if we pull the camera further away from it. Though the box is still falling at the same rate, because we are much further away from it, now it appears to fall much more slowly. We often observe large creatures in film from a similar distance. The final area we're going to look at is inertia. This applies to all objects, but especially large, or as we'd say in physics, massive ones. The inertia of an object is the tendency of the object to remain at rest, or if in motion, to continue its motion. So what does this mean? Well, let's look at an example. Consider a man standing looking at a rock. The force required to get the rock moving forward will be much smaller than to get a large boulder moving in the same direction. Now if we take a similar example but substitute the ground for ice, it will be much easier for the man to stop a rock from moving than a large boulder. This is why small objects like insects and little people can change direction very, very quickly, while large or massive things find it much harder to do so. Now a quick test. I'm going to show 3 pillars falling over, and I want you to decide which one's falling at the correct speed. A, B, or C? If you've been paying attention, you'll probably realize it was a trick question. Let's look at the objects again, but this time with something else in shot to give us a sense of scale. So next time you see something like this, you'll realize it's not just the rubber suits and bad acting that make it look wrong.